Now we're going to take it the next step. We're going to look at different types of reactions and then focus on stoichiometry for solutions. They're a special case. And in fact, solution stoichiometry can be easier, I think, because it follows a pattern, which will become obvious later. All right, now we haven't talked about polar molecules, but this is sort of an introduction. The solubility of substances depends in the large part on the polarity of the solvent or the major component and the polarity of the solute, which is the minor component. For instance, if we were to make salt water, you just add table salt to water, goes into solution pretty readily because salt is an ionic compound and it can break apart into ions. And those ions are readily hydrated by water molecules. And the figure on the right of the screen there is of a water molecule with, notice, one oxygen and two hydrogens bound together. This is a molecular compound. In other words, those are covalent bonds holding oxygen and hydrogens together. And for reasons that we'll talk about in more detail in a later chapter, the molecule is bent. And what that does is, we'll also talk about this. I don't think we've talked about, no, we haven't covered periodic trends yet. So just take my word for it for now. Oxygen is, the term is electronegative. Oxygen is more electronegative than hydrogen, means it draws electrons to itself. So we use an arrow with a plus on one end to show you this is the positive end. And I use that, this is the small Greek letter delta, which means it's not a full charge. It wouldn't be something like this. Right. That's a full charge. In other words, it lost an electron to get that. This one, this delta plus just means that the electron density shifted away from it. It gave it a slight positive charge. So that's true for both hydrogens. And then the electron density accumulates around the oxygen. What that does is it creates a polar molecule, a polar referencing magnets here, north and south pole. We have a positive and negative pole. So we have a slight negative this side and a slight positive that side. Well, when we put an ionic substance or even a polar substance, another polar substance in water, it associates with these readily. So if we were talking about sodium here, sodium would be like this, and it would form an attraction for that side. And in fact, lots of other water molecules will gather around it too. But that aids in creating the solution, this polarity. And of course, I don't know if you've heard it before, but water is often referred to as the universal solvent. Nobody's heard of that? Somebody has? Yeah. It's not really, but it does dissolve a lot of stuff. It's just not universal. Oh, we got a video. See that? This was made in Canada, so it's going to have French along with it too. That's a water molecule. The small positive ones are sodium The large blue ones are chloride. New surfaces are exposed and the water just keeps go right in there and grab some more. Okay. That also emphasizes the point that ionic solids are electrical insulators. In other words, you can't get a current across a crystal of sodium chloride. I've seen some of them, they grow big things like that. Pretty, actually. But you put an electrode on either side and your light bulb doesn't light because those charges are not mobile in the solid form, in the crystal form. They're locked in place. When you put it in solution, I mean, they're free to move. So that's why the only way to get an ionic solid to conduct electricity is either put it in solution of some kind or melt it. Now, these aqueous solutions are characterized by a solute. A solute is the minor component. For any solution. And the solid is the major component by convention. Now, there are situations where you can start off with a little bit of solute and just keep adding it. And eventually you'll have more solute than you do solid. But we still hold on to the solute, even though it becomes a major component, it's still the solute. For instance, table sugar, water. You know, you put a lot of that in solution. I mean, it's easy to make a hummingbird feeder juice with 50-50 mix of table sugar and water. But you can go higher than that. Okay, so but one of the other things about the solute-solvent relationship is you can have multiples. You can have lots of solutes. You don't need just one. You can have more than one. But the solvent, you can only have only one. Only one solvent. You can have lots of solutes. An electrolyte is like sodium chloride. It's a substance that you dissolve in water will now allow the solution to conduct electricity. You know, pure water is an insulator too. If you have a low voltage source and you stick your electrodes in water, it won't conduct electricity. If you have a high enough voltage, then the situation changes. With a high voltage, you can ionize the water and then you can get it to move. So that's why I say don't stand in a puddle of water in a lightning storm, because there's enough voltage there that it'll make water conductive. And of course, your body is conductive anyway because you have lots of these electrolytes in it. Okay? When you get your medical report, blood analysis, urine analysis, it'll have a section called electrolytes. You have sodium, potassium, magnesium, calcium, chlorides, various other types of these ionic species. And they're operationally defined, as they say. They're electrolytes because we say they are. They conduct electricity, which is our definition. All right, there's a difference between strong and weak electrolytes. And this is chemical definition. A strong electrolyte is a substance that dissociates into movable ions. Almost completely, we could say completely dissociates. Into ions. So that means it's a very good conductor of electricity. Whereas a weak electrolyte is only partially, or we might even say minimal, dissociates. Right? An example of a strong electrolyte would be sodium chloride. Right? Completely dissociates. A weak electrolyte would be something like a weak acid, like vinegar. Acetic acid would be a weak electrolyte. And then there are non-electrolytes that no matter what you do, they'll go into solution, no problem, but they will not conduct electricity. And table sugar is a good example for non-electrolytes. I think I've got a video coming up. Yeah.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity. We know from various...
You want to see that again? Okay, so if we're going to focus on reactions that occur in solution, many of them do. It's very useful medium for reactions because once your reactants are in solution, they're free to move around and you get complete interaction between the different reactants. Whereas if you had two solids, then the reaction depends on how finely divided the solid is. Case in point would be coal dust in a mine. It's very finely divided. You mix it with air and all you need is a spark and you got an explosion. Well, of course, that can happen, or you can hit a gas pocket and the result's the same. So in order to describe a chemical reaction in solution, we need to know first the nature of the reaction. What type of reaction is it? And then the amount of the reactants that are present. So they will determine whether or not the reaction proceeds, the rate at which the reaction proceeds. So we need a way of expressing the concentration. One of the most commonly used ways of expressing concentration is molarity. Molarity is the number of moles, and I use a small n here, with no zero up there, right? If I put a zero up there, that's a neutron. But this is N stands for moles. Right? This is moles of solute per liter of solution. Okay. Very convenient method of expressing concentration. Because if you know that in our example there, 3 molar hydrochloric acid, 3 molar HCl, we should have an aqueous out here. 3 molar HCl, we know that if I have a large vat of, and I know the concentration is 3 molar, and I take a liter out of it, I know that I instantly have 3 moles of hydrogen chloride in that solution. And it's like any other equation, right? You have 3 variables, 1, 2, 3. If you know 2 of them, you can solve for the other one. So that example solves for the molar concentration because we know that value and that value. What if we have 500 gram sample of potassium phosphate? Oh, got another 0. 500 gram sample of potassium phosphate. This is where you have to know how to write it. Write the formula for potassium phosphate. Right? Potassium, phosphate. There's nothing up there phosphate. It's a polyatomic ion. That's phosphate. It has a 3- charge. This has a 1+ charge because it's an alkali metal. It's always a +1 charge. So that means we need 3 of these to balance that 3-. That's your formula. If you dissolve that in enough water to make this volume of 1.5 liters, then what's the molar concentration? Right? We can't do it directly from here because that's mass, it's not moles. So what we need is the molar mass of this compound to find out how many moles there are. Right? Dimensional analysis says we need grams on the bottom, moles on the top. So if we calculate the molar mass of potassium phosphate, we have 39.10 times 3 for the potassium, and that's grams per mole. And then we have 1 phosphorus, and then we have 4 oxygens. I already know that. Phosphorus I have to look at 30.97. Okay, add those together. Let me see if I can save time if I've already done it. Yeah, 212.27. So that goes right here. That many grams per mole. Remember, all conversion factors are equal to 1. So this may be grams per mole here. But if that's a conversion factor, just flip it. And that cancels the grams and leaves you with moles. And the moles are 2.355. So here we have 2.355 moles divided by 1.5 liters equals what molarity? I don't have to finish it. 1.57. So we know with 500 grams in a solution that's made up to 1.5 liters, that's not, you don't add 1.5 liters of water. You make up the volume to be that value. Because first of all, we don't know the volume of this. And second of all, when you put that much potassium phosphate in 1.5 liters of water, you may get 1.5 liters, you may get more than or less than. There's no way to know. My guess is it'll get really cold. Okay, so in this case, we have how many ions? When that goes into solution, what does it do? It breaks up into 3 potassium ions and 1 phosphate ion. So its ion concentration is actually 3 plus 1 is 4 times that value. 4 times 1.57 would be the ion concentration in that solution. Right? That's important, especially for a medical profession. Right? If you're supposed to make up a solution that's isotonic with your patient's body tissues, then if you make up the solution in terms of molarity of this salt, then it's going to be 4 times as concentrated as it should be, right? And all their red blood cells are going to go that. And soon after the patient dies. And then you have years and years of litigation. All right. So that's what this slide is about. Calcium chloride breaks up into 3 ions. So we can say that the calcium ions in this case would be where the molecular concentration is 0.25 molar. The calcium concentration is the same because there's only 1. And the chloride concentration is twice. But if you add them together, you have 0.75 molar ions. Okay. Which one has the solution has the greatest number of ions? Okay. I guess I should do this. I don't think I have it animated. I just have the answer there. Okay. So in this case, we're going to use Henry Ford. We used Henry Ford before. Yeah. So if you have 400 milliliters of a 0.1 molar solution of sodium chloride, remember, molarity equals moles per unit volume. So if you want to know the moles, solve for N is M times V. This is M, this is V. So if we multiply those two together, we're going to get the moles. Actually, we get milliliters times molarity is millimoles. Okay, thousandth of a mole. So we would get what, 40.00 millimoles of sodium chloride. Okay, we do the same thing for each one of them. Times 0.1 molar calcium chloride. And that would be 30 times 0.00 millimoles of calcium chloride. Now, I haven't answered the question yet because it says the greatest number of ions. This is the number of moles. Why don't I go ahead and do the ions? So this is going to be times 2 because there are 2 ions for every millimole here. So this is going to be 80 moles of ions. And this is times 3. 1, 2, 3. That's 60 millimoles. Then we have 200 milliliters times 0.1 molar iron 3 chloride. So that's going to be 20 of this one times 4. You have 4 ions when it goes into solution. So 4 times that's 80. And then the last one. Did I do that right? 200 times 0.1 is 20. Yeah, 20. 4 is 80. Is this one right? 40 times 2 is, yeah, okay. And the last one is 800 milliliters times 0.10 molar sucrose. All right, that's going to give us 80 millimoles of sucrose times 0 ions. Right. So that one comes out 0 ions. Because sucrose doesn't dissociate.
Second one's 90, but 60.
Yeah, thank you. Yeah, that makes more sense. Especially when I show the answer. That's 2. That's 1, 2, 3. That's 1, 2, 3, 4. Okay, so yeah, take my word on the millimoles for now. I'll prove it to you later. So a little bit about problem solving. We don't need to spend a lot of time here. Actually, you just need to practice it. First thing you do when you are presented with a problem is say to yourself, what's the question? What am I trying to answer? And then you think about, how do I get there? Sometimes it's a very simple one-step process. Sometimes it takes several steps. So you think about that, because sometimes the problem is so complex that you can't solve it with a single calculation or a single reasoning. And you got to logically break it apart into pieces, into manageable pieces. Then you bring those answers of the pieces back together to find the end product. And that comes with experience. That's why I give you so many problems to work, because only if you're diligent about working a lot of problems in chemistry, this is going to remain a mystery for the rest of your life. So the point is, the solution with the greatest number of ions is not necessarily the one which has one in which the volume of the solution is the largest or the formula unit has the greatest number of ions. Right? You have to do the calculation. Now, here's a very practical discussion. I used to analyze soil samples, hundreds of them at a time. We extract them and take and filter the extract. And usually I'd run it through an atomic absorption spectrophotometer, which would tell me the elemental composition. Or later on, when I worked for people that had more money, I'd use an inductively coupled argon plasma spectrometer. But the result was the same. And since I was going to analyze lots of samples, I had this specific formula for the solution that I used to extract the soils. Only if I made them up fresh every day, it would be a big carboy, like a 10-gallon carboy, and I'd have to make that up fresh every day. So what we chose to do was we make up a solution that had the right ratio of all the components, only it was extra concentrated, right? As long as everything would stay in solution at those concentrations, we were good. Then when we wanted to prepare a working solution, we just dilute it, because the ratio, we just add more solvent to a certain amount of the concentrated, and the ratio of the components would still be the same. So here's why dilution works. If I have a stock solution over here of a given concentration of molarity, okay, and I want to dilute it to say, let's keep it simple. Let's say I have a 1 liter volumetric flask here. So there's your mark that says 1 liter. Okay. And I want a particular molar concentration over here that's less this one. So I need to take out a volume here. Take that volume out. Not the whole thing, just a subsample. And I put it over here. Okay. This volume 1 becomes this volume 2. And they're both the same. Oh, excuse me. My mistake. Volume 2 is here. Volume 2 is the total here. So this small volume is going to go into this big volume. Okay. How many moles did I take out of here? Right. Number of moles equals molarity times volume. We used that in the previous example. How many moles ends up over here? This is the solute, moles of solute. How many moles of solute end up over here? Exactly the same. So that N2 is equal to this N1. So the number of moles over here can also be expressed as that this new molarity times the new volume. Right, this total volume times the molarity of the solution will give us the number of moles that we put in there. If N1 equals N2, then M1V1 equals M2V2. That's why it works. Sometimes, in fact, your book may have it like this. The concentrated molarity times the volume of the concentrated you take out equals the molarity of the diluted one times the volume of the diluted.
Really, that's.
Yeah. M1 V1 equals M2 V2. Okay. But that's why dilution works. And this is the animated version. We won't to spend a lot of time on this. It all works because the moles I saw you took out of here are the same moles you put in there. Okay. I'm sorry, I'm going to have to skip this. Otherwise, we're going to run out of time. All right. I think this is the dilution problem coming up. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide? Okay. So I found that when you have a word problem like this, and you know there's going to be a calculation involved, extract the information and put it in some recognizable form. Right? What do you give it? Well, the molar concentration you start with is 2 molar sodium hydroxide. The molar concentration you want to end up with is what? 0.8. Okay. By doing this, when you plug the numbers into your formula, you put them in the right place. If you just try to extract them there and shove them in the formula, you may get them in the wrong order. And wrong order means wrong answer. Okay, what else are we given? We're going to make 150 milliliters of this one. So V2 is 150 milliliters of this one. What we need to know is how many milliliters of this one to take out and dilute to this value. Okay, so now we have the ability to do this calculation. And notice that if we put the molarity on one side and the volume on the other side, what happens to the units? The units cancel. So we can stay with milliliters. We don't have to change it to liters when we have this type of ratio. And the nice thing about that also is our answer is going to come out in milliliters. Okay, so if we solve V1, M2 over V2, M1 down here, and M2 is 0.8 molar, and V2 is 150 milliliters, and then M1 is 2 molar. Okay. So can we do that one again? Let's see. 2 and a 0.8 is 0.4. A tenth is 150 is 15 times 4 is equal to 60, right? 60 milliliters. See if I did that right. Animations. Yeah. Whenever possible, I like to do those in my head. It keeps my mind from going to mush. Okay. These are major types of reactions. And we classify the reactions by what they do. And these classifications have been built up over the centuries, actually. And what you'll come to realize as we proceed through them is that some reactions can be classified as multiples. Right? For instance, I'll just point one out. Combustion, the very last one at the bottom. Combustion is also an oxidation reduction reaction from the top. All right, so that's the list. We're going to talk about them individually here. A precipitation reaction is also called a double replacement. So in generic form, if we have a compound like that, and of course it's an aqueous solution, to simplify it, and we combine it with this solution. In other words, they're separate until we pour the solutions together. Then what happens? Well, a double replacement means that this is the cation, that's an anion, cation, anion. Now this cation is intimately mixed with that one, so this cation can interact with that anion. So we have the potential for producing that. And then this C with that B. Okay? One, usually just one, will form a solid and precipitate, drop out of solution as a solid. And let's just, for argument's sake, let's say this is the one that does it. Whereas this one stays in solution. That means that the C and the B, anion, cation, started off in solution here, they end up in solution. So they didn't do anything. The reaction is driven by A plus D makes the solid. And when you make the solid and it drops out of solution, it's no longer readily available in the mixture. That's when we say it drives the reaction. This typically occurs with ionic compounds, some ionic compounds in aqueous solution. Right, here's an example. Barium nitrate and potassium chromate. So we have the barium now has the opportunity to interact with the chromate. And when it does, it forms a solid. Whereas the nitrate and the potassium, when they interact, they could care less. I mean, their potassium nitrate is perfectly soluble. And in fact, I think I've got did I hand out that solubility chart? We've got
This
it.
one right here.
Yeah, that one. Okay. Okay, good. All right, so there's an example of a precipitation reaction, which is also a double replacement reaction. Let's see. I think I like this one because it's pretty. Sodium chloride in one, silver nitrate in the other. What happens when we mix them? Okay. You instantly get a solid. Now we have silver and chloride interacting, and it's a solid. That white precipitate is the solid. And then, of course, you have the sodium nitrate, which is perfectly soluble. So the business of this reaction is that one plus that one makes this one. Okay, I've got another one coming up. There it is, in close up. Different. Silver and thiosulfate are in cycle. Barium and sulfate. But anybody knows, anybody had a barium enema? Barium sulfate, that's what they use. As a, they fill you up with that stuff and then do x-rays. It's very good at attenuating x-rays. But it's not soluble, so your body doesn't absorb it. So it's perfectly safe. All right. That's enough. That's enough fun. So for now, at least in this semester, we're going to distinguish between soluble and insoluble. When we say insoluble, in fact, that solid that precipitates may be slightly soluble, but we're going to treat it as if it's insoluble for now. And when we get to the second semester, we'll talk about how to quantify that solubility. I think that's next semester. And to keep things simple, we're going to talk about solubility in terms of water as the solvent, right, in aqueous solution. There we go. Now, these are the rules for solubility. If you were chemistry majors, you have to learn those rules. And I had to do that one time. But since you're not chemistry majors, right? No chemistry majors in here. Okay. That's why I latched on to this solubility chart. So that you can learn how to use that solubility chart, then you can tell whether a combination of a cation and an anion in aqueous solution is soluble. You just have to follow it. I think I've got on a separate slide here. Excuse me. Let me move down here. There it is. So in order to use the chart, you just run across the top until you find the cation and then go down until you find the crossover from anion. And if it's clear, it's soluble. If it's grayed out, then it's insoluble. Okay. And then I've got the general rules down here too. If you ever decide to use these rules, they're set up in order for reasons. If you have a conflict between two of the rules, and you're trying to decide which one takes precedence, the one above is the one that wins. Okay, so let me go back. Here we go. Oops. So which of the following ions form compounds with lead 2+? That is soluble in water. Well, if you look at your chart, lead 2+ and sulfide is insoluble. Chloride. Let's see, we're looking for the soluble ones, right? Yep. I think lead chloride is insoluble also, isn't it?
Right.
Yeah. So that one's insoluble. This will be a 2 here. How about nitrate? Nitrate. So we need 2 of them because this is a minus. That one is soluble. Yeah. This one is soluble. And the rules, if you learn the rules, find that all nitrates are soluble. Every one of them. Sulfate is insoluble. Lead 2 sulfate is insoluble. And then the last one is thrown in there just to see if you're paying attention. Because you're not going to form a compound between 2 cations. Okay. So the one that we found that was soluble was the nitrate. Now, when we write these equations, at this point, we've used what's called the formula equation, or some places you might see the molecular equation. Molecular equation is misleading because these are not molecules. Right? These are ionic compounds. They don't form molecules where you have covalent bonds. Formula equation is proper. So with this one, silver nitrate plus sodium chloride, I drew that one earlier, forms silver chloride, solid, and sodium nitrate, aqueous. Right? Then you balance the equation. Right? Use your budget method. In this case, it's simple. Right? There's just one of everything. And it's already balanced as written. Right? That's so that we can illustrate the question without having to worry about the mechanics of balancing it. Then we realize that what happens in aqueous solution is that this silver nitrate is not AgNO3, it's Ag plus in aqueous solution and NO3 minus in aqueous solution. So what we need next is the complete ionic equation. So we separate the ions, right? Ag plus aqueous, NO3 minus aqueous, Na plus aqueous, Cl minus aqueous yields AgCl solid. And you still got sodium aqueous and nitrate aqueous. That's the complete ionic equation. Did you see how we moved from one to the next? You just break the ionic compounds apart because that's the way they are in solution, actually. Then we look at this one and say, all right, what have we got on both sides of the equation that are exactly the same? The nitrate's the same on both sides, isn't it? And the sodium's the same on both sides. So you can cancel those out. Right? They're not, I mean, they're still there, but the reaction itself, the driving force of the reaction is the silver and the chloride together make silver chloride. So then we have the net ionic equation, in which we cancel those common terms out. What that tells me is that if I go into my storeroom and I want to conduct this reaction with silver and chloride, say I don't have sodium chloride, which would be kind of strange. But if I don't, I can use potassium chloride just as well. If I don't have silver nitrate, say I have silver, let's see, what's another soluble silver compound? Acetate? Yeah, that one. Silver acetate would work, right? Because the acetate and the potassium are also soluble, and they would be net cancel out. So you can conduct that reaction with different compounds. Oh, those guys that we canceled out, they're known as spectators. They're just sitting around watching things happen. This is another example where we have cobalt 2 chloride and sodium hydroxide forms cobalt hydroxide, cobalt 2 hydroxide, and sodium chloride. And then we separate the ions, the complete ionic equation, and then we find the common terms and cancel those out. And the net equation is the cobalt 2 plus ion, the hydroxide ion, and the solid cobalt 2 hydroxide. Now, sometimes you'll end up with a net ionic equation that can be reduced further. Example, in this case, suppose we had 2 CO2 pluses and 4 OH minuses and 2 COOH2s. Then we reduce it to 1, 2, and 1. So that's a trick that we often use in the multiple choice questions to catch you off guard. Okay, so now we're going to move to stoichiometry of these precipitation reactions. First thing you have to do is identify the species in the solutions and determine what reaction occurs. Typically, what happens in these solutions, if there's a solid form, it will drive the reaction toward the solid. If there's a gas formed, it will drive the reaction toward the gas because the solid is removed by precipitation, the gas is removed by bubbling out. And that drives the reaction toward that side. Then you write the balanced equation and reduce it to the net ionic equation for the reaction. Then you can calculate the moles of the reactants. Right? If you have a solution, we're following similar procedure to stoichiometry we've done before with solid reactants. Only now we have to find the moles before we can move from one place to another in the reaction. Same rule, has to be moles. So instead of finding moles by converting the mass of a reactant to its moles, we find out how many moles of the reactant there are by the volume times the molarity. So you're going to the same place. You go into moles before you can move. And then if you're given 2 reactants and absolute amounts of each one, you got to find out which one's limiting. Okay. And we didn't do an example of that. We ran out of time, I think. And my slide set didn't have any. But there are examples in the worked problems. And we'll, since I'm going to run out of time, we'll get to those next what is this, Thursday. All right, we'll work some of those problems. And then do what the problem asks you to do. All right, once you find out the moles, usually in a precipitation reaction, you're going from knowledge of the reactants to the solid precipitate. So find out how much precipitate is formed. The problem may ask you for moles. It may ask you for grams. If it does for grams, then you take the moles and convert it using the molar mass of the compound. All right, and we already talked about that already, how to use it. Okay, let me see how far along we are. Quite a few. I've got 1:45. I got maybe 25 minutes. All right. If we have 10 mils of 0.3 molar sodium phosphate, that's one of our reactions. Sodium phosphate. This is a 3 minus, that's a 1 plus, so we need 3 of those. This is in aqueous solution. And while we're here, we'll just say we've got 10 mils of this, and the concentration of the solution is 0.30 molar. Yes. And we're going to react that with lead 2 nitrate. All right, so it tells us that the charge on lead is 2 plus. And the cation, the anion is nitrate with a 1 minus. So that means we need 2 of those. Okay. And this is in aqueous solution. Okay. What precipitate will form, first of all? Well, we know that these are separate ions. So we look at this cation, this anion, and this cation, sodium nitrate is completely soluble. Just look it up in your table. Sodium nitrate is soluble. Okay. Lead plus phosphate, look that up in your table, it's insoluble. Phosphate, PO4. This is a 3 minus, this is a 2 plus. So how do you get that to balance? Remember? Cross multiply. Bring the 3 over here and the 2 over there. All right. And this is a solid. Okay. Let's see, we're going to have to balance this equation. Maybe I better prove this out a little bit. There we go. All right. Let's see. I didn't put that much up. 20 milliliters here of 0.2 molar. 0.2 molar. There we go. Okay. The precipitate formed is lead 2 phosphate. All right. So that answers the first question. Lead 2 phosphate. There we go. The balanced molecular equation for the reaction. Let's go back to the question. What mass of precipitate will form? Okay. So in order to find out how much that is produced from this mixture, first of all, we need a balanced equation. Right. And you can set up your budget with phosphate and nitrate as balancing units, because they're not broken apart in the process. So we should have, let me see if I can do this without that. If I put a 3 there for the sodium, that makes 3 nitrates. Let's see. That's not gonna work. I thought it was gonna be easy. Okay, so let's do sodium, phosphate, lead, and nitrate. So we got 3 sodiums here, 1 phosphate, 1 lead, 2 nitrates. On this side we have 1 sodium, We have 2 phosphates. We have 3 leads and nitrate, 1 nitrate. Okay, where do we start? Why don't we start with lead? Yeah, let's start with lead. We got 3 on that side, we need 3 on this side. So that makes 3 here. And that gives us 6 nitrates. Okay. Now we need 6 nitrates on this side. But now we have 6 sodiums. 6 sodiums. Now we need 6 sodiums on this side. So we need a 2 here. 2 times 3 is 6. And 2 phosphates. So that's 2 and that's 6. Now we're balanced. Okay. Takes practice. In fact, I fall back to the when I see that it's not going to balance easily, it's going to take me several steps, then I'll go back to my budget too. Okay, now that we have this balanced equation, we can determine which one of these is limiting. Right? Okay, so the way you do it is you say how many moles of this are formed. Molarity times volume equals moles, or in this case, milliliters is millimoles. So this is 3.00. 3.00 millimoles. And this one is 4.00 millimoles. Okay. So the way you do it is you say, all right, how much of this can form from that many millimoles of sodium phosphate? So 3.00 millimoles of sodium phosphate, and our conversion factor is coefficients. Right? So we want to cancel this one and leave us with this one. Right? And the magic numbers are 1 for this one and 2 for this one. So 2 divided into that equals 1.50 millimoles of lead to phosphate. Okay, because these 2 cancel. That's how much you could produce if this were not limiting. Right? Once this runs out, that's how much you would produce. Let's do the same thing for this one. Right? In this case, we've got lead nitrate, lead 2 nitrate, and we want to convert that to lead 2 phosphate. Right? Magic numbers 1 here and 3 here. So 3 into 4 is equal to what? That's 1.33, isn't it? 4/3. 1.33 millimoles of lead to phosphate. Okay, so which one produces the least amount? This one. That's the limiting one. And that makes this one excess. Okay, now that we've calculated, this is actually how much is produced, because it's all used up and produces that much. Then we've got the moles. Yeah, we've got the moles of lead 2 phosphate. So we just need to convert that back to grams, right? Isn't that what it was asking? What's the mass of our precipitate? But, right, millimoles is not one of the units. We want grams per mole. So 3 leads is what? Let's see, lead is over here. 207.21. 207.21 grams per mole. And let's see, how many phosphate How many phosphorus do we have? 2. We have 2 phosphorus. That's 30.97. And we have how many oxygens? 2 times 4 is 8. 8 oxygens. Right. We add those together. Where's my calculator? I put it. Pocket. Must have been left over from yesterday's class. All right, so 207.21 times 3. And then 30.97 times 2. Add those together, and 16 times 8. Add those together. I get, oh, is that right? Let me do that again. 207.21. 3 times. That's 622. 30.97. Okay, and then 16 times 8. That's better. I must have hit a wrong decimal somewhere. 11.57 grams per mole. All right, so if we're going to convert millimoles, how many moles is millimoles? Millimoles. Here's the way I do it. What does milli mean? Milli means 10 to the minus third, doesn't it? So 1.33. I'm going to take that milli out here and make a multiplier out of it. That's how many moles we got. Okay. Now I can convert that to grams. I just need moles on the bottom, grams on the top, because I want to cancel those two. So 811.57 times 1.33 exponent minus 3, and I get 3 significant figures, 1.08 grams of lead 2 phosphate. Okay. There's our precipitate balanced equation. Moles of the reactants. There we go. Then we find out which one's limiting. Right. We find that this is the limiting reactant. So we only produce that much. And then we convert that many moles to 1.08 grams. Okay. All right. Now, before I erase that, we got another question based on this same problem. What's the concentration of nitrate ions left in solution after the reaction is complete? Concentration of nitrate ions? Well, nitrate ions don't precipitate. They're still in solution. All of them are still in solution. So how many moles of nitrate ions have we produced? Well, we've got 4 millimoles of this compound, but 2 nitrates for every one. So how many millimoles is that? 2 times 4 millimoles equals 8 millimoles of nitrate ions. Okay. The thing that's changed is the volume, because nitrate was in this volume at first. Now it's in this one plus this volume. It's in 30 milliliters of volume. And you'll find out that millimoles divided by milliliters is molarity. So 8 divided by 30. Let's see what that is. 8 divided by 30 is 0.2 0.67 molar nitrate. Now, do you believe me that millimoles divided by milliliters is molarity? What if we do what I did before? Take that millis out here. Milli is that, right? Milli is this, -3. You got it on the top and the bottom. Millis cancel. Now you got moles divided by liters. That's molarity. Okay, let's see if I did it right. Yeah, 0.27. Rounded off to 2 places. Now, I'm not sure if we do. Do we do the next one? Yeah, what's the concentration of phosphate ions left in solution? In this case, what we've done is we've got excess phosphate over here, right? This is excess. And we're going to use up some of it to make that, but there's going to be some left over in solution. Okay. So I got 6 minutes. Let's see, I'm going to have to let the slide do the talking for me. So there are 0.0030 moles of sodium phosphate present to start, or that many millimoles. That's what we're saying. So how much of the phosphate is used? Well, over here, we've got 1.33 millimoles of this, which is how many millimoles of phosphate? 2.66 millimoles of phosphate were used up because there are 2 for every 1, right? We got that many millimoles used up. How many millimoles of phosphate did we start with? We started with 3, right? Because there's only 1 phosphate for this concentration. So 3 millimoles of compound is 3 millimoles of phosphate. So we're going to use up, out of that many millimoles of phosphate, we're going to use up 2.66 millimoles. Right. So we have 0.34 millimoles of phosphate left over. Okay. And it's in the same volume, 30 milliliters. So divide 30 into 0.34. So I get 1.13 times 10 to the minus 2 molar. That close? 0.011. All right, so let's move it over 2 places, 0.0113 molar. So round it off 2 places, it's 0.011. That's the concentration of phosphate left in solution because it was excess. Okay. See, furrowed brows and deer caught in headlights. Okay, other types of reactions. All right, I got 5 minutes. So we can do what we can, and I can come back and finish the lecture without you once I get you started on the lab. Or we can keep going till we finish and then hope we can get the lab done before it gets too late. Acid-base reactions. Acid-base reactions, right? We know from our nomenclature, we know what an acid looks like, right? It's got a hydrogen here, at least 1, maybe more. And then something else attached to it. And then a base is going to be something over here and hydroxyl. Okay, when they react, you get this X and Y together. Sometimes they precipitate, sometimes they don't. This cation with this anion. But the hydrogen and the hydroxyl always get together and form water. That's what drives an acid-base reaction, formation of water. So that's why the net ionic equation for an acid-base reaction is this one plus this one yields this one. All acid-base reactions are boiled down to that. Oops, sorry.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Okay, so that acid-base reactions are also known as neutralization. For acid-base reactions, we can rely on that net ionic equation, or you can use the complete molecular equation for an acid and base, especially if you want to keep all the species intact when you're doing the calculations. For instance, if we have phosphoric acid and we want to react it with sodium hydroxide, then you've got 3 hydrogens here and only 1 there. So what we're going to end up with, of course, is water, right? That's always a product. Plus, in chemical terms, we end up with a salt. Chemical salt is the product of an acid-base reaction. You got water, and then everything else is the salt. We have sodium and phosphate. In aqueous solution. All right, so to balance this equation, we need 3 of those. And that's it. That'll do it. All right, 3 hydroxyls and 3 hydrogens gives you, well, 3 waters. Right? And you add them up. All right, we got 3 hydrogens here, 3 hydrogens there, 6 here. We've got 3 oxygens here, 3 there. Got 3 sodiums, and we've got 1 phosphate on the other side. So that's balanced. And from that point on, once you got the balanced equation, the stoichiometry is the same. Right? If you've got concentrations here, then you can work your way to the other side. Just like we did before. You got to have moles to move. All right. Acids and bases. You don't just have to dump them together and witness the reaction. You can actually control the amount that you add of one to the other. We call that a titration. In a titration, you usually have one of them that you know, let's say, we know this concentration is, let's make up a number. Let's say it's 0.2 molar, that one. We don't know this concentration. That's unknown. So if we take a known volume of this one, say 20 milliliters, and we add enough of this to neutralize that, to bring it to neutral pH. And it might be a little basic, but we bring it to the equivalence point. The equivalence point where the reactants, this amount is equal to that amount in terms of this chemical reaction. Then we reach the equivalence point. Then we say this volume, whatever this volume is here, let's say it takes, I don't know, 60 milliliters. Right? Then we can calculate this concentration, right? Because molarity times volume equals molarity times volume. Well, actually, it's not that simple because we got 3 of these. But the titration says that with this known one, we can add just enough of this to reach the equivalence point, and now we can calculate the molarity. Because once we know this one, if we say 0.2 times that is what, 12 millimoles of this, how many millimoles of this does it take to neutralize that? Well, the ratio is 1 to 3, so it takes a third of those. So actually, it's 4 millimoles of this one are required to neutralize 12 of those. So if we know 4 millimoles here, and we know this many milliliters, then we can divide by 20 and say, let's see, 2 divided by 10, that's, let's see. 4 divided by 20 is 2 divided by 10, or 20 divided by 100. That's not going to help me. This is millimoles per milliliter. Oh, it's a fifth, right? Is that right? It's a fifth. 0.2 molar. So it's the same concentration. All right. We'll do a titration later, and then it'll become hands-on and easier to understand later in the semester. Oh, we'll make this point. The equivalence point is the exact point at which the number of hydrogen ions and the number of hydroxyl ions are equal. But if you've got 100 of these titrations to do in a day, and I've had to do that before, you use a simpler method. You use a color change indicator. And that indicator changes color very close to the equivalence point. So close that the error is minuscule. And that way you can run your titration up to the color change, stop, check the volume, move on to the next one. Okay. For the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid? All right, the relationship here is 1 sulfuric and 2 sodium hydroxide. Why do we know that? Because there are 2 hydrogens here. We need 2 hydroxyls to make 2 waters. And then sodium sulfate. So 2 sodiums here, 1 sulfate, 2 hydrogens and 2 hydroxyls make 2 waters. Right? Hydroxyl, hydrogen, hydroxyl, hydrogen. That makes 1 water. This makes the other water. 2 waters. Okay, just in case it whips like that. Okay, now that we know that, if we have 1 liter of 0.5 molar sulfuric acid, 1 liter, 0.5 molar sulfuric acid, 0.5 times 1 is equal to 0.5 moles of sulfuric acid, right? But the ratio is 1 to 2, so it takes twice sodium hydroxide to neutralize this much sulfuric acid. That means it takes times 2 is 1 mole of sodium hydroxide to neutralize. Okay. Now, another type of reaction that's extremely important in chemistry is called the redox reaction. The long version is oxidation reduction reaction. We shorten that to redox. All right. First of all, the principal defining characteristic of a redox reaction is that electrons are transferred during the reaction from one place to another, from one species to another. And I'm going to repeat this. I don't know if I've said this before, but I'm going to repeat it anyway. What does oxidation reduction mean? Well, I use an acronym. Oil rig. So oxidation is loss, and that's loss of electrons. Reduction is gain of electrons. And when electrons are transferred, they don't just sit out there in space. Right? In a chemical reaction, electrons are transferred from one place to another. So if one species loses electrons, somebody else has to get them. Right? They always work in pairs. If you have an oxidation identified in a reaction, there's always a reduction that goes with it. And one way to recognize this is number 2 here is a helpful hint. If you're trying to identify an oxidation reduction reaction, and we haven't covered how to do it based upon oxidation states. We're going to do that in just a minute. But if you have a reaction like, let's say, you have, this one. No, that's not right. Yeah, that's solid. And you add aluminum to it. And you heat it up, you get iron plus aluminum oxide. Okay. That's a very useful reaction. It's called thermite. But the point I want to make is if you have on one side or the other, you have an element. And on the product side, in this case, you have that element is in a compound. You are guaranteed that that is a redox reaction. Or if you have the element in a compound on this side and it's an element on that side, you have a redox reaction every time. Okay, that was just an example. Okay. So, our example here of a redox reaction is sodium and chlorine reacting to produce table salt. So we have sodium solid, that's a metal, plus chlorine gas. And if they react, we get sodium chloride. Okay? Now, based upon that hint I just gave you, here is an element. It's in a compound here. Here's an element. It's in a compound there. So we know right off the bat that this one is a redox reaction, but it's not balanced yet. We need 2 chlorines over here. That makes 2 sodiums. Now it's balanced. Okay, so what has happened in the process? Well, we know from past experience that over here, this is a positive ion, that's a negative ion. So how did they get that way? Well, this one's neutral, right? That's where the charges go. That one's neutral. So what we've done is we transferred an electron from here to here. In fact, since there are two here and two there, we actually transferred two electrons. That's how chlorine got to be chloride and sodium got to be the cation. Sodium cation. All right. That is an example of a redox reaction. Now, if you don't have this easy way to figure a redox reaction like element to compound or compound to element, you have to use oxidation states. All right, so we're going to talk about that next. What do we mean by oxidation state? Oxidation state. Oxidation state is a bookkeeping scheme. In fact, it works for metals, it works for nonmetals, and it in compounds also. It also works for type 3 compounds where you don't have ions. Because it's a bookkeeping scheme, we don't have to create ions to calculate the oxidation state. The oxidation state tells us what has transpired for an element when it goes from one side to the other of a reaction. If its oxidation number changes from one side to the other, then it has either undergone oxidation or reduction. So first we need the rules. The oxidation state for an element in its most stable form is 0. So if we had sodium solid, its oxidation state is 0. If we have chlorine gas, its oxidation state is 0 for each one of the atoms in that molecule. Right? This is a diatomic molecule, but each chlorine is an oxidation state of 0. Now, once we create an ion like that, its oxidation state is the charge. So this oxidation state is 1 plus or plus 1. The oxidation state for this one, since it's gone to that, is a minus 1. Right? Minus 1 plus 1. Right? Those are the easy ones. Now, when you find the third rule, when you find oxygen in a covalent compound, such as water, its oxidation state is assumed to be minus 2. Oxidation state. That's not a charge, right? It's our bookkeeping scheme. This is an oxidation state of minus 2. So what does that mean the oxidation state of hydrogen has to be? It has to be plus 1. Because oxidation states have to zero out for neutral compounds, right? So 2 pluses and a minus 2. Now, those are not charges. I say it again. Those are not charges. Those are oxidation states. So the rule 4 refers to this hydrogen. This hydrogen in covalent compounds is nearly always a plus 1, especially if it comes first in the compound. It's a plus 1. Now let's go back to oxygen. There are some cases where oxygen is not a minus 2 in peroxides. If we had this one, H2O2, this would be a plus 1 or a plus 2 total. That means this one has to be a minus 1 to be a minus 2 total. So in peroxides, and if we draw the structure, right, this whole group is a minus 2. So each one has to be a minus 1. Okay, that's the exception for oxygen. This oxygen, in a peroxide, oxygens are -1. All right. See, we're down to rule 4, I think. Rule 5, fluorine is always -1, no matter what compound it's in, whether it's an ionic compound like this one, it's -1. Sodium's a +1. Or if it's in a covalent compound like hydrogen fluoride gas, it's a -1, and that's a +1. Okay? Fluorine. Now, the other halogens, they can be -1, especially if they're combined with a metal. But if they're combined with a nonmetal, the other halogens combined with a nonmetal in a covalent compound, then we have to make some assumptions, and I'm not going to bore you with those right now. We'll cover those when we work problems. We'll encounter a couple of those. Rule 6. Rule 6. The sum of the oxidation states for neutral compounds is 0. All right? If you have polyatomic ions, then the sum of the oxidation states must be the charge on the ion. For instance, if we have nitrate with a minus charge, that's a polyatomic ion. Well, oxygens are going to be -2 each. 3 times -2 is -6. What does nitrogen have to be to preserve a -1 charge? It has to be a +5. Right? That's the only way you can add this to that and get -1. All right, so let's see if we can do oxidation states for these examples. K2Cr2O7. Right? You should know how to name that. It's a type 1 compound because potassium has a fixed charge. Right? So that's potassium. Cr2O7, dichromate. Right? So this potassium dichromate, we want to know the oxidation states of each of the elements. We know that potassium has to be a +1. It's an alkaline metal. It's always +1. Right? So that means +2 total for the potassium. How about oxygen? Oxygen's a -2. So 7 times -2 is -14, right? So what do we got so far? -2 and -14 and +2 is -12. Right? It has to be a neutral compound. So we need +12 for those 2 chromiums. That means each chromium has to be a +6. And that will keep the compound neutral. I think I've got it animated here. There we go. How about this polyatomic ion? Carbonate. Right? We know that oxygen is a -2. Times 3 is a -6. But we don't want to neutralize all of the minuses. We want to keep 2 of them out. Keep 2 minuses out for that charge. That means we only have to neutralize a -4 with a +4. So carbon is +4 and oxygen's a -2. All right, how about the next one? MnO2. We'll do the oxidation states before we name it. Okay, MnO2. We know this one is a -2. That means -4 total. And it's a neutral compound, so this one has to be a +4. Correct? Okay. So if we name it now, it's manganese, type 2 compound, manganese 4 oxide. Okay, PCl5. That's a type 3 compound, right? Both nonmetals. All right, in this case, I mentioned earlier that we didn't know what to do with the other halogens. Fluorine is always -1. In this case, we're going to go with a -1 for chlorine. If we don't make an assumption, right, like that, then we can't calculate the other one. So we're going to go with a -1 here. That means -5 there, and this has to be a +5. So when you're faced with a compound, a covalent compound that has a halogen in it, go with the halogen for the fixed charge as -1. And I say charge, I should say oxidation state. Fixed oxidation state for chlorine will be -1. That makes phosphorus +5. And then the last one. And this would be phosphorus pentachloride. And the last one, SF4. All right, we can go with fluorine as -1 because that's the rule. So we have -4 here, this has to be +4. And this is a type 3 compound, so we have to say sulfur tetrafluoride. Okay? And there are the charges for that one. So we're using the rules to determine the oxidation state, not just for its own sake, but so that we can now do this for a chemical reaction and determine which way and how many electrons are moving in that reaction. Okay. I mentioned this one earlier. We got to transfer electrons. The transfer may occur to form ions, but it doesn't have to. Oxidation is loss. So when you lose an electron, what happens to the oxidation state? If your oxidation state is 0 and you lose an electron, that means you've increased by 1 positive. Right? So oxidation will go toward the positive. You increase your oxidation number. Whereas reduction we're losing an electron here, 1 or more electrons. And here, we're gaining electrons. So reduction, this increases oxidation number. Oxidation number. This one decreases. Right, you're going more negative, which is a decrease. Let's see. Definitions. Reducing agent, oxidizing agent. Let me see if I've got an example here that'll work better. Example. Yeah. Okay. So let's work with this first one. A. So you have zinc metal plus 2 hydrochloric acid yields hydrogen, zinc chloride, zinc 2 chloride in aqueous solution plus hydrogen gas. Okay. Now we know this is oxidation reduction reaction because that's an element It's in a compound here. Hydrogen's in a compound here, it's an element there. So we know this is oxidation reduction. So let's determine the oxidation states for each one of the elements. These elements are going to be zero. That's rule number one. Chlorine's going to be a -1, hydrogen's a +1. Chlorine here is a -1, which is -2 total. That means +2 here. All right, so we've done our oxidation states. Now, let's trace the movement of electrons. If this is 0, and that's a +2, what had to happen? If we go from here to here, we had to lose 2 electrons for every zinc. Okay? Loss of electron is oxidation. Okay? So this is oxidized. Okay? Hydrogen, chlorine, it goes from -1 to -1, so nothing happened to chlorine. But hydrogen went from a +1 to a 0. This had to gain 1 electron per hydrogen times two hydrogens equals 2 electrons times 1 equals 2 electrons. Okay, this is reduction. All right. Now, one other term that's been introduced on the previous slide. Remember, since these things happen in pairs, oxidation and reduction always happen together, then this oxidation is caused by this reduction. This oxidation is caused by that agent, which is the oxidizing In other words, this is the cause of that oxidation. And by the same token, this is the cause of that reduction. So this is the reducing agent. Okay? Those are 2 new terms. All right, let's look at B. Let's look at B and see if it is. Cr2O7 2-. This is an aqueous solution. And then we're going to add hydroxyls in aqueous solution. And that's going to produce 2CrO4 2-. Goes from dichromate to chromate. And then this is aqueous plus water. Liquid, pure liquid. Okay, oxidation states. Let's see, we don't have any elements in here. Notice one thing also. This is an anion, that's an anion, that's an anion. Where are all the cations? They're not written. They're there. You have companion cations in here, but they're spectators. So we're not going to write them in. Okay, so let's take oxygen. -2 plus 1. Okay? -2 plus 1 gives you a minus. Okay? -2 times 7 is -14. We hold 2 of those negatives out for the charge. -12 is what we're going to balance with a +12 here. That means each one is a +6. How about over here? -2 times 4 is -8. We're going to hold 2 of those out for the charge and neutralize the other 6 with a +6. Okay, notice +6 chromium, +6 chromium. -2 oxygen, -2 oxygen, -2 oxygen, -2 oxygen, +1 hydrogen, +1 hydrogen. This is not a redox reaction. Right? It's a reaction, all right, but there were no transfers of electrons. So this is not redox. Okay, and the last one, C. Two CuCl, two CuCl. This is aqueous. Yields CuCl2. This is aqueous plus Cu solid. Yeah, is that balanced? 2 copper, 1, 2, 2 chlorine, 1, 2. All right. I'm going to make an observation first. This is what's known as a disproportionation reaction, where you get one reactant to go 2 different directions. Now, the same molecule doesn't go both directions. You got one molecule goes one direction, one goes the other direction. All right. So in this case, we've got 0 oxidation state for that one. We've got a -1 here, which is a -2 or a +2 there. On this side, we have -1, and this is a +1. So one of these coppers goes this route with a loss of 1 electron per copper times 1 equals 1 electron. The other one goes this direction. Okay? And that's a gain of 1 electron per copper times 1 equals 1 electron. Okay? One thing I didn't point out in a previous example was when you transfer electrons, the losses must equal the gains. So if we transfer 1 electron this direction, we have to transfer the other electron that direction. Okay. So if this one is gain, it's reducing. That means this is the oxidizing agent. And the other one is the reducing agent. So one of these is the oxidizing agent, one of them is the reducing agent. And when they react, they produce this and that by means of electron transfer. Okay. All right. Balancing oxidation reduction reactions by oxidation states. Now let me see. Yes. Okay. This is going to be the next step to the budget method. So let's take a look at an example. All right. These in green, these are the steps. But I'm going to take those steps and show you an example. Balance the reaction between solid zinc and aqueous hydrochloric acid to produce zinc 2 chloride. This is a 2+. This is a 1-, so that means we need 2 of those. Okay, and hydrogen gas. Now, we could balance this with just a straight budget method, and it will work. But there will come a time when you have an equation that will not balance easily by the budget method. And those are always redox reactions. So the method I'm going to show you now takes advantage of redox to aid us in balancing the equation through budgets. All right, so the first thing you do is oxidation states. Well, the first thing you do is write the compounds correctly. Right? Zinc metal, hydrochloric acid, zinc 2 chloride, and hydrogen gas. So balance this reaction. Well, that's a 0 oxidation state. This is a 2 plus, this is a 1 minus. This is a 0. This is a plus 1, this is a minus. Okay, so what's happening? Well, zinc is going from 0 to plus 2. How did it do that? It lost 2 electrons per zinc. Okay? Hydrogen goes from a plus 1 to a 0. So it had to gain 1 electron. Gain 1 electron per hydrogen. All right. These have to balance. You got 2 up here and only 1 down here. Well, what we also know is that there are 2 hydrogens here. So times 2 would be 2 electrons. But that's only 1. You only got 1 electron from here, so we need 2 more. I mean, we need 2 electrons that balance here. Times 1 equals 2 electrons. Now the electrons are balanced. Now, if the electrons are balanced, we look to see if the other elements are balanced. Sometimes they are, right off the bat. 1 zinc, 1 zinc. 2 hydrogens, 2 hydrogens. 2 chlorines, 2 chlorines. We're already balanced. Right? There's our starting place. And in this example, what they've done is they've separated the zinc and the chlorine. And this might actually make more sense because this is what happens in solution. Oxidation states of each one. There we go. Gain and loss of electrons. All right. And we'll put in our tie lines again. Now we need 2 in order to balance the 2 electrons. That means we need a coefficient of 2 in front of the hydrogen chloride. And we need 2 chlorines also. All right. So that's a rudimentary balancing technique using the oxidation states and the rules for redox equations. At some point down the line, we're going to balance equations using half reactions. I'm pretty sure that's coming. Let me see. No, I'm sorry. Half reaction method comes second semester. So you've got a reprieve until you come back for more. All right, so that's it for chapter 4, types of chemical reactions and solution stoichiometry. That, we just skimmed the surface. What you need to do now is get into the review document and try as many of those problems as you can. So that when we come back 2 days from now, we can work out some real life problems that extend beyond what we've studied here.